Okay, guys, we're gonna slide in two more concepts. This is a very, very, very intense session. These slides are like a lot of information. So if you need to stop and take a break and then come back, please do. We would be going over this much more slowly probably in class. So I apologize for that, but we'll be working with it quite a lot. So hopefully that'll help. Okay, now half-life. Remember, going back to half-life. Half-life is what we use to determine how long it takes to get rid of half of the drug, and it's very important to determining our dosing interval. As you recall, and I don't know if you remember this, but way back we were saying how we dose approximately every half-life. As a rule of thumb, half-life is correlated to our dosing interval. So usually we dose about every half-life. That's a good rule of thumb. We'll have a Cmax to Cmin ratio of 2 to 1. And that's usually good for most drugs. So we need to understand what's happening with half-life. If we look at clearance, then we know that our clearance, if our drug is cleared by the liver, we're going to look and see how clearance is going to change our half-life, not only our CSS average, but our half-life. Recall that our volume of distribution is, our VD is approximately equal to VS. This is VD apparent volume of distribution, and this is volume distribution at steady state. We assume these are approximately equal, and we know that these things determine VSS, volume of plasma plus volume of tissue, times a fraction unbound in plasma over fraction unbound in tissue. So if we can say that our volume of distribution here is really equal, so we can leave in the VP, but this plus makes it kind of hard. We'd like to have all multiplication so we can cancel things. Our volume of plasma is relatively small and probably doesn't change much. So I'm going to discount the volume of plasma and say it's really about this piece right here as far as your actual volume changing and what the determinants of the volume are. So if we take this piece and put it in here where the volume distribution was, we can say now that our half-life is dependent upon 0.693 times our tissue volume, which again is probably going to stay pretty constant, times our fraction unbound in plasma and our fraction over our fraction unbound in tissue. There's our volume, and here's our clearance. So will you buy that? Are you good with this? So we can really have a good idea. We can put in here really what determines our volume distribution as part of our half-life. Okay, we're going to need this going forward, so I just wanted to go over that idea quickly. All right, another idea that we need to go over quickly before we can do our predictions is CSS free versus CSS total. Recall that our free concentration, in order for a drug to be active at the pharmacologic site, it cannot be bound to a protein. It must be free. If it's bound to a protein, it cannot interact with the pharmacologic binding site. So in order to determine this is our actually active concentration. So our active drug at steady state is our CSS free. It's not our CSS total. Our CSS total is bound plus free, right? Our free concentration plus our bound concentration. In order to get our free concentration, we can take our total concentration and multiply it times our free fraction. Remember, fraction unbound is a fraction. So let's say, for example, let's say we have a drug C. Now I'm not going to say C because C is too confusing. You're going to see all these C's around here. Drug R that is 90% bound. So it's 90% bound. So what does that tell you? That tells you the fraction unbound is what? 10%. So we would write it as 0.1, wouldn't we? So if our fraction unbound is 0.1, if you know that, and you know that the total concentration is 10 milligrams per liter, what's the free concentration going to be? If you know it's 10 milligrams per liter and 10% of it is free, you know that the free concentration is 1 milligram per liter, right? What did you do? You multiplied the free fraction times the total. So I just want you to buy this equation too, that free concentration is going to be equal to our total concentration times fraction unbound. All right, we need both of those concepts. And then we're going to go into our predictions of what's going to happen with all this, which was the whole point of doing all of this work. I hope you'll understand once you see it. Thank you. Well, I can't do that, I guess, with this.